previously we've covered magnetic interactions with a magnet and charges moving in that magnet. So we have a magnetic field and we have moving charges, and these experience a magnetic force based on the direction they're moving. So QVB, Q's, V is this way, B is the magnetic field, which is also this way. This would experience no force, however, is moving, for example, this way, and the magnetic field was pointing this way, then it would be going not into the screen but out of the screen because it's a negative charge. So it would experience a force in that direction. However, this is not the only type of magnetic field interaction. It is fundamentally the only interaction that occurs, which is the Lorentz interaction, the Lorentz force. However, there are less apparent places where it occurs. Like for example, if we have a empty wire loop here, and we start moving this magnet towards it, or we rotate this wire loop away from the magnet, the fact that a current appears in this loop doesn't seem intuitive from our moving charges model. So essentially, there's a formula that states, which is Faraday's law, that the induced electromotive force in a loop is equal to the number of loops times the derivative, or the absolute value of the derivative, I guess this is all absolute values, of the magnetic flux with respect to time. So magnetic flux, as you should remember, is equal to the double integral of magnetic field dot product the area vector. Closed flux has this circle on it, but magnetic flux is a property that does not necessarily need to be closed. It's just that when it is closed, it has a value of 0. But there can be flux through a surface, and that flux can be positive or negative and non-zero. So this is the formula for flux, and we have, this magnet here presents some magnetic flux that's producing through this loop. And the rate of change of that induces a current in the loop. So if, for example, this magnet was moving towards the loop, let's use a different color marker, maybe blue, I have literally all the colors in the world here. If this magnet was moving towards the loop, then there would be some current induced, or an electromotive force creating a current induced through this loop. And this loop is this is an empty loop, it's just a piece of wire. So it's surprising that moving a magnet would just suddenly create a current in this loop. I was stunned by it the first time I heard about it, but this actually happens because of the same force, the Lorentz force that we talked about. And if we just illustrate it in a different light, we can make it clear exactly why this occurs. But this Faraday's law is a more generic application of the Lorentz interaction, which governs electricity and magnetism. So if we have this loop again, and then we have a magnet, just to make it pretty, I'll put the south as blue. And this magnet is moving towards the loop. This instead could actually just be thought of as the loop is moving towards the magnet, because motion's relative. And if we imagine that this loop contains a bunch of positive charges and a bunch of negative charges, then suddenly we have a bunch of charges moving in this magnetic field. And long story short, the positive charges are going to be pulled this way, clockwise or counterclockwise, I'm not really sure which one. And the negative charges are going to be pulled the opposite way, which is going to create an electromotive force in the loop. So this measurement of magnetic flux changing really just represents a bunch of microscopic Lorentz force interactions that are harder to measure on an individual aspect. So yeah. If we have a loop here and we have a magnet, this loop rotating will create a change in magnetic flux, or this loop expanding will create a change in magnetic flux, or just a increase in the magnetic field by the magnet strengthening or moving towards the loop. That will also create a change in magnetic flux. So when we're calculating d magnetic flux, dt, we'll use whatever specific formula for the magnetic flux through that surface. And the general one just might be d, for example, BA cosine theta dt. And whichever one of those changing variables is the one you need to differentiate. The other ones can just be moved out as constants, unless you have multiple changing variables, in which case you might need to use the chain rule. So if, for example, only magnetic field is changing, then we'd have dV dt times a cosine theta is equal to the magnetic flux, or the derivative of the magnetic flux. Or if the area was the one changing, then we'd have dA dt, and B is out in the constants. If both these were changing, then we'd have dA dt b cosine theta plus dB dt a cosine theta. And then, obviously cosine would be changing too, and then suddenly we'd have d cosine theta, which is sine of theta, or negative sine of theta, times BA. Yeah. Or I guess, theta might be changing at some certain rate, but, it doesn't matter. So, right. Electromotive force is equal to, or the magnitude of electromotive force is equal to the derivative of magnetic flux with respect to time. If you have multiple loops, then they each will have a electromotive force, and therefore the electromotive force is going to be equal to n times the derivative of magnetic flux with respect to time. This n term is similar to the n we saw next to the I term in the previous lecture. So yeah, that is the formula you need to memorize. Alright, and now I'm going to provide a derivation for this formula. Or not exactly a derivation, but more of a representation for how it works in a situation that we could apply multiple methods to solve for the electric field in. So let's say we have a circuit that looks like this. I could use a better pen. I got my double-sided pen. That's terrible. So we have an electromotive force from the battery, not to be confused with the induced electromotive force. This is just battery. And remember, EMF in the circuit is always just going to be equal to the sum of the EMFs. And that's because delta V is always equal to sum of delta V by Kirchhoff's law. So yeah, we're going to have a loop that looks like this. Maybe we have a resistor also. So remember, when we're calculating the induced current by Faraday's law, we simply take the induced EMF and divide it by resistance, because according to Ohm's law, V equals IR, or epsilon is equal to IR. And therefore, we can just divide both sides by R, and suddenly we have I is equal to EMF over R. Okay, so back to our circuits. We have a resistor, we have a battery, and we also have, in this scenario, which is not common, an external magnetic field coming from somewhere. And we have a physical mechanical piece. We have a moving rod. This moving rod is going to be sitting on the circuit. You can just imagine, like, we have some really hard wire and we have a steel rod which is ready to roll. And this moving rod has some velocity. Okay, so let's call the height of this moving rod, maybe we'll call it H, and maybe we'll call this length. So now we have length VH. I think that's enough constants, and except for B, which is the magnetic field. So now we're going to try to derive the induced EMF created by this rolling rod. And to make things simpler, I changed my mind. We're going to eliminate the battery. Okay, so let's say that first of all we're going to solve this with Lorentz force. This is going to be kind of an unintuitive derivation, something you don't often see, but this is a valid way to solve the equation with Lorentz force. So let's say this rod has a total charge Q and a charge distribution lambda. And remember, because it has a height h and lambda is equal to Q over L, or in this case h, we have lambda times h is just going to be equal to Q. Okay, so as this rod is moving, it has a velocity v this way, and there's a magnetic field pointing into the screen this way. So bop, bop, wait, bop. There we go. Our force is going to be down. So we know that force equals QVB on whatever charge is inside of the rod. And then let's rearrange this equation so we have force divided by charge on the left-hand side. So now we have force divided by charge is equal to velocity times cross product, the magnetic field. So we have this vector here is going to be pointing down, and therefore this vector here is going to be pointing down. And if you recall correctly, force is equal to Q times E vector. So if we divide both sides for this equation, we have force divided by Q is equal to the electric field. So suddenly we have electric field is equal to velocity across B for this scenario, which we have some uniform charge distribution on the rod. So there's an electric field now being pulled down on the rod because it is moving in this magnetic field. And finally, one more equation. We know that the derivative of electric potential with respect to x is equal to the negative of the electric field. Or you could say the other thing, the negative derivative of voltage with respect to x is equal to the electric field gradient. If we integrate both sides of this, so let's move the negative sign back, and we'll move dx to the right-hand side. This is a little bit of a not rigorous way to do this, but integral both sides, we have the voltage potential difference is equal to the negative integral of electric field with respect to x. I mean, this really should be a dot product here. And now we have electric field is equal to V cross B. So we have the voltage across this rod, rolling rod, is equal to the electric field of the rod, or the negative integral of electric field of the rod, dot product dx, and this integral will boil down to E times x, where x is h, because h is the height, the distance across we're integrating this electric field. And I guess there might be a negative sign, but for this purpose it doesn't matter. So we just derived, finally, electric field is equal to VB in this case, and we're only worrying about the magnitude. So we have VBH is equal to the voltage across this rod. So by this rod rolling in this circuit, we will induce a voltage. The rod moving through the electric field creates an electric field. Sorry, the rod moving through the magnetic field creates an electric field potential across it, and that total potential is going to be equal to the velocity times the magnetic field times the height of the rod. So if the rod was half as tall, then it would have a less voltage. If there is half as much magnetic field, or the rod is moving half as fast, we'd also have less induced current for this circuit here. So yeah, this is the classical derivation of that. And the other derivation of that is with magnetic flux. So instead, if we use Faraday's law, EMF, by the way, this was an EMF, is the absolute value of which is equal to the derivative of magnetic flux with respect to time. Then we have, if we calculate for magnetic flux here, which is equal to magnetic flux is equal to BA cosine theta. Cosine theta in this case is 1 because they're perpendicular to each other. The magnetic field is directly piercing the area. The area is just going to be equal to length times height, which is LH. And the derivative of all this, well, the magnetic field is staying constant, so we don't have to worry about that. The height is also staying constant, but the length is not staying constant. As this rod is moving to the left, the length is going to be increasing by the velocity. So if we take the derivative of this, that's going to be equal to the derivative of length with respect to time times b times h, and the derivative of length with respect to time is going to be equal to v. This was the derivative. And poof, we have the same formula as we calculated with the other method. So this is just sort of a visualization proof for the way that Faraday's law applies to, any system, and you just choose which way to interpret it. You don't interpret with both Lorentz force and Faraday's law. You sort of choose one way to calculate the amount of induced current or electromotive force around a loop. All right. So Lenz's law. We have a wire loop, which we'll just represent with the rectangle. And we're going to have an increasing magnetic field. Okay, so we have, this is initial, and here's final. So let's just use stupid units. Let's use B equals 1 something or other, maybe 1 Tesla, I guess. And then we have area, let's say this is just 1 meter squared. So the final flux...
How did the area become 0 there?
Oh yeah, sorry. 1 meter squared. The final flux, or the initial flux, is equal to 0 Webers. And the final flux is equal to 1 Weber. A Weber is a Tesla meter squared. Okay. So we'd say that, let's say this transition happened in 1 second. So imagine someone takes a magnet and they're like, okay, we're going to put some, I guess, if this field is going into the screen, then it would be a south pole. They would be pulling a south pole towards this loop, and that would be changing magnetic flux through the loop. So this is going to induce a current. We have E is equal to negative d flux dt, and we're going to drop the n because we have 1 wire loop. In this scenario, that would be negative 1 Weber per second, which is equal to negative 1 volt. So we'd have negative 1 volt of EMF that would be induced by this change in magnetic field. But for Lenz's law, we're looking to determine which way this current is flowing, because we currently don't know that. It's kind of hard to determine. The thing is, flux is not a vector. Flux is a scalar, which makes this problem sort of more difficult because you can't really do it with simple vectors. You have to do it with a law itself and actual like conceptual thinking. So Lenz's law states something rather complicated, and that's that the direction of an electric field induced by a change in magnetic flux is such that the magnetic field created by the induced current resists or opposes the initial change. All right, that's Lenz's law. This sounds ridiculous. It doesn't make any sense.
Wait, the direction of an electric field induced by a change is negative flux such that
It is
the magnetic field created by the induced current
opposes the initial change. Yeah.
What?
What exactly? All right. So let's imagine we don't know which way the induced current goes yet, but let's just like guess. Maybe it's this way. It either goes right or left, or clockwise or counterclockwise, and we have to determine. So this induced current created by this change in magnetic flux also creates its own magnetic field. So which way would the magnetic field be for this current? It would be going out of the screen above and into the screen below. So look at that. This red arrow creates a magnetic field that opposes the change in magnetic flux.
Okay, actually that makes sense.
It's kind of cool. It's kind of
that
weird.
opposes.
Yeah, because like no, the one by the electric current is coming out of the page at the top,
Yeah.
and the thing that's the electric flux is inducing the change in electric flux is going into the page, and so they're opposing each other.
This current
Oh.
acts to like sort of maintain the original magnetic field. Like we currently had no magnetic field, and suddenly magnetic field comes into the equation, and the thing is like, we don't want magnetic field. So it creates this current to keep this initial magnetic field
It's
and
like
slowly transition out of it.
Oh.
it's like inductance for magnetic field.
Yeah.
Okay.
So essentially, whenever you're doing one of these problems, you're gonna use like some weird right hand rule to figure out the direction that you want. So you're like, okay, the magnetic field change is going into the screen. So it's looking like this, but then we want it to oppose that. So we want to go like this, and that means the induced current is going to go like this. This is the direction of the induced current. It's going counterclockwise because that would create a magnetic field into the screen opposing this initial change, which was into the screen. I mean, out of the screen. Opposing the initial change, which is into the screen. Alright. Let's do another practice problem.
Yeah, keep it there for a second.
Keep it there for a second. Okay. And this is probably like the hardest concept, I think, in electricity and magnetism.
Really?
I mean, there's some weird formulas. I
Bro,
think this is one of the worst. There's some examples that get a little bit harder, but it's like conceptually sort of cool.
Is this why inductance happens?
I mean, like on the surface, this looks like easy to understand, but if you like try to think about like exactly why it happens, it's kind of complicated. That's what I'm saying. Yeah, inductance happens sort of because of conservation of energy. Essentially, the magnetic field and the electric field act like in harmony to sort of like smoothly transition in and out.
Oh.
Yeah.
Act like harmony.
Yeah, in harmony.
Oh, and so like.
Okay, can I erase this? Can I erase Lenz's law? Or erase Lenz's law? Okay, so let's give a more complicated example. Because this is simple. This one's just the magnetic field is the same direction as the change in magnetic flux. But you can't treat this as a vector, you have to think of it conceptually, and I'll show you why. Let's say we have a different loop, and then we have a second one and it's small. The loop changed size. Same density. The loop simply shrunk. The actual magnetic field didn't change. Again, this is initial, this is final. Which direction would current be induced when this loop changes size?
Same way, bro.
No, because then some of it would actually be not resisting. Because like right here, that's going out of the page here and then into the page here. And so that's not resisting, that's helping it. You know what I'm saying?
Alright, okay.
Fuck you, right? No, wait, listen.
Yeah.
Because the electric field is like this.
Oh, he's right. No, that's true though.
It's the change in magnetic flux that we're looking at. And we're trying to oppose the change in magnetic flux.
Yeah.
So the magnetic flux from here, let's say magnetic flux is strong, and magnetic flux here is weak. Okay? There's less magnetic flux because there's less area. How do we try to maintain the same amount of magnetic flux? Would we want to increase the amount of magnetic field X here or decrease the amount of magnetic field X? We want to increase the X. So we'd aim to have a magnetic field going into the whiteboard when inside the loop, and that would create a current this way.
So Lenz's law means that like it wants to keep the same flux.
It wants to keep the same magnetic flux.
Oh.
It acts to resist the change, or it wants to keep the same amount.
Oh, okay.
Alright. And like if we change this example here, if we change this to like a lot of magnetic flux, so let's say we had 2 Teslas, 2 Webers, then even though this magnetic flux is pointing into the screen here, it's not opposing the direction of the magnetic field, but it's opposing the change in magnetic flux. So this would go this way. We want more X's. So we got.
Do we have to
the
go
difference?
to dinner now?
No, I don't have to. That's for my brother. But see the difference between magnetic field direction and change in magnetic field direction? This is opposing the change in magnetic field, even though it's pointing the same direction as the magnetic field. We had more magnetic field initially, and less now. So we want to maintain the same amount of magnetic flux. That's why I'm saying sort of conceptually hard to understand. It's the change in magnetic flux, not the magnetic field that you're trying to maintain.
Oh, so wait.
That's not
Oh,
conceptually
in this
yes.
example, the loop is shrinking, and it's not the magnetic, like, it's not the field that's changing.
Right.
Instead, the
Right.
loop's
Anything that
expanding.
changes the magnetic flux will induce a current, not just changing the magnetic.
That makes more sense.
So yeah, think about this, but just remember Lenz's law and remember E is equal to negative d flux ct, and you'll be able to figure out the direction of an induced current.